Good morning. So the first thing I wanted to talk about today is I want to talk about this proof that the ratio of convergent sequences converges to the ratio. The quotient converges to the quotient. It's kind of like a quotient rule for sequences. So last time a couple days ago, we talked about how we needed to show that a n over b n minus l over k, an absolute value, was less than epsilon. That's what we needed to work towards. So I don't want to put together the entire proof here, but I do want to make sure that we're understanding how to overcome kind of the different technicalities that arise and how this one's slightly different than the product rule. So when we look at a n over b n minus l over k, the first thing we do is find common denominators. So we get something like a n times k minus b n times l over b n times k. And this is going to be where our first problem shows up, this b n in the denominator. So the next thing is we need terms like, here let me switch colors here so you can tell the difference in my scratch work. But we need things like a n minus l to show up and b n minus k to show up. The reason is we know a n converges to l, we know b n converges to k, so these are the two quantities that we can make as small as we want. So we need these terms to appear in order to make the quantity we have small. So we always got to be going back to those things we know, and those are two things we know. So in order to get those to show up, we can add 0 to the numerator. So we have an a and k, and what if we added in, say, an lk, subtracted and added an lk to both terms? Now, when we group and factor, we can get an a n minus l from these first two terms here, and we're left with an extra k, and then over here in the second two terms we have a bn and a k when we factor out. So that'll give us exactly what we need in terms of these two quantities over here. So the way that factoring looks is we can write it like this. So we can say it's absolute value, we get a k, and then an a n minus l, and then I guess minus, we'll go with minus L when we factor that out, then we have a b n minus k. That minus won't hurt us because we're going to use the triangle inequality here in a second anyway. And then we have b n k in the denominator. So the k and the l in front of the a n minus l and the b n minus k, those really don't hurt us at all. It's the denominator, the b n in particular, that we have to really watch out for. We know k is not 0, but we got to figure out how to deal with those bn's. Okay, so let's move on here. The next thing we're going to do is use the triangle inequality to break these two terms in the numerator up. So let's go ahead and move over here and do that. So we have, it'll be less than or equal to, we'll have, bring the k out front, so it'll be absolute value of k times a n minus l, and then plus we had absolute value of l times bn minus k. Remember, it was minus, but when we take the absolute value and use the triangle inequality, that can go away. All that's divided by, there's an absolute value of bn and k downstairs. Now, we could go ahead and take the absolute value of both terms in the denominator, cancel out at least the k's in the first term, so something like this, a n minus l over absolute value of bn in that first term. The second term, we still have an l, we still have a k, and we have a bn minus k. Oops, and I forgot, we also have a bn in the denominator as well. And that's really where the problem occurs, or the difficulty occurs in this problem. So let's go ahead and talk about that. The L's and the K's over here on the right don't really hurt us in any way. I mean, we can make bn minus k less than epsilon over something to deal with those extra that extra L and that extra K out front. what we really have to do is get that bn out of the denominator, because our epsilon, we can choose to be whatever we want, and that gives us an n, which would be fixed. Like if it was b capital N, that would be okay. The problem here is we don't have that. We have b lowercase n, and b lowercase n is variable. It can change, and as n gets bigger. Remember, n is any number past capital N, whatever we choose that to be. So we have to take into account that there's some but this isn't a changing number, right? And when we choose our epsilon, it has to be a fixed number that we're going to use. So let's kind of take a little detour here, and let's talk about how to find a bound for bn, a lower bound for bn. So here's the way we're going to go about it. Remember that because bn converges to k, that means for all epsilon there exists a capital N such that bn minus b is less than that epsilon for all n greater than or equal to capital N. And so we can choose whatever epsilon we want here. We know bn converges, so we don't have to show that. We get to use that, and that's the big distinction here. And so we're going to make a careful choice. I shouldn't say bn converges to b here. Let's erase that. Bn is supposed to converge to k. So we can choose whatever epsilon we want, and the epsilon that I'm going to pick is I'm going to do this with epsilon equals the magnitude of k over 2. And it turns out that's going to be the epsilon that allows me to come up with the bound that I need. Okay, so let's look at the following thing. If we make that choice of epsilon, then we get absolute value of bn minus k is less than absolute value of k over 2. Now, that's actually not quite the form I want to use it in. I want to use the consequence of the triangle inequality, which allows me to say that the absolute value of bn minus absolute value of k is less than absolute value of bn minus k, which I know is now less than absolute value of k over 2. Now, the advantage of that is that if I remove the inequality, the absolute value from the inequality on the left, I get minus absolute value of k over 2 less than absolute value of bn minus absolute value of k, which is less than absolute value of k over 2. Now, I can add the modulus of k to all sides of the inequality, and by doing that, I end up with modulus of k over 2 less than or equal to modulus of bn, absolute value of bn, less than or equal to 3/2 absolute value of k over 2. Now, the upper bound here really isn't that important. I mean, we knew bn was bounded from the get-go. The point here is that I have a lower bound. I know that all of the bn's are greater than or equal to the absolute value of k over 2. One thing I should emphasize here is when I made this specific choice of epsilon, I really know that this is true for all n greater than or equal to some capital N, say n1. So I have to go far enough out in the sequence that this is true. This isn't true for all n, but there is a point where it is true. And why do I know it's only true for those? Well, it's because I used a specific choice of epsilon. So for every epsilon there exists a capital N such that from some point forward we have the statement of convergence. So I now have an n1. I've used the convergence of bn once to know that if I go far enough into the sequence, I can find a lower bound for bn. The advantage here is now when I take reciprocals, I have an upper bound for the absolute value of bn. And that is what I'm going to need as I move forward. Okay, let's put this all together and kind of see what choices we're going to have to make. So remember, we were here. We had absolute value of an over bn minus L over k. We said this was less than or equal to, we had an an minus L over absolute value of bn. And then we had absolute value of L over absolute value of k, absolute value of bn, that was all in the denominator, and then we had, sorry, let's clean that up here. We had bn minus k in the numerator, like that. Now, we know that if we're far enough into the sequence, we know that the 1 over bn's are less than 2 over k, absolute value of k. So we pick up 2 and then absolute value of k plus, and then over here on this one we get a similar kind of thing. So we're getting a 2, the L. Now we have k squared, and then we still have a bn minus k. Now, we're finally at a place where we can finish this out. So we know that we can find there exists, a different color here. We know that there exists another n, say n2, such that an minus L can be made less than whatever we want. So it looks like maybe we want, say, epsilon over 4 absolute value of k. Seems like that would do the trick. And we know that there exists an n3 such that bn minus k is going to be less than, what do we need here? Epsilon times, I have my k in the wrong place up here on A. We'll go back and fix it. Epsilon times absolute value of k squared over 4 absolute value of L. Seems like it would do the trick. Probably need to watch out here that, excuse me, that the L isn't 0. I could fix that by doing 4 times absolute value of L plus 1. That would avoid any kind of divide by 0 problems. I know k is not 0, so I don't have to worry about it there. Let's go back and fix our am. So we had less than 4 times. I should put the k up here. Okay, so let's go back and then to see how that helps. If in this first term we have a 2, we have an absolute value of k, the an minus L we know is less than epsilon times absolute value of k over 4. Over here on the right term we have 2 absolute value of L over absolute value of k squared. Bn minus k we know is less than epsilon absolute value of k squared over 4 absolute value of L. The nice thing here now is that the k's cancel on the left-hand term. The 2 over 4 becomes a half. On the right, the l's cancel, the k's cancel, and so ultimately I'm getting epsilon over 2 from the first term, epsilon over 2 from the second term, which makes the whole quantity less than epsilon. So there are a few more details that you're going to have to work out when you actually go through your proof. This is, it's a very complete scratch work, and actually almost all of this will show up in the proof somewhere, but we still have to go back and organize it in the right way. So let epsilon be greater than 0. You're going to have to assert that there's an n1 with the desired property, and n2 with the desired property, and 3 with the desired property. Tell me which n you're going to pick. Suppose n is greater than or equal to that capital N, and then show me that all of this actually works. So hopefully that helps kind of get over the hump there, especially that part with showing that there is a lower bound for B, and if you go far enough out into the sequence, that's kind of the maybe the most delicate part of the argument, which you're allowed to read as tricky if you want, but it's the most delicate, and least obvious. So hopefully that helps everybody as you get moving forward, and helps kind of illuminate this. As you work through your corrections. So, but again, make sure you focus on not just kind of recreating this part of the argument, but making sure that all those kind of parts of the definition are kind of verified in your proof. They're all in the right order and in the right places. You don't kind of leave anything out. So let's really just strive for this one to really just have a whole bunch of super solid proofs as you move forward.